Here we go. Okay, so today, as you know, we've been, if you had a chance to do the workshop, and I hope you did, we are working on mapping. The idea here is that this is our second class on visualizing results. And by this point, you have learned about how to wrangle data, how to model data, how to simulate data. And now you may be wondering, well, what's left? And the answer is more of everything that we've already done, right? You've really built the main toolkit for data analysis. And so now the rest of data analysis is just using these tools that you've already used with some add-ons. So for instance, today, you're going to find new ways to data wrangle a different type of data. You're going to find new ways to visualize a different kind of data. And then you're going to model the results from that process, right? So these are three things that we've done. We're just doing them with a new type of data. So what is that new type of data? Spatial data. Courtney Page Chan spoke with us a little bit about this last week, and she actually very nicely prepped this whole topic for today. I was really delighted about that. Up until now, we've been working with data frames, which, as you know, are the R equivalent of spreadsheets. But there are some types of data that when you kind of pause and think about it, you might wonder, how do you encode that in a data frame? Geographic data fits into this issue. How do you represent something on a map in a data frame? And you kind of have to, right? Because if you want to compile a huge data set of geographic information, you're going to need to find a way to get it into a data frame. So some of these are more intuitive than others. Points. You may already know that any place on Earth can be represented by a longitude, latitude coordinate, kind of like an XY coordinate, but on the face of the Earth. For example, we've got 3 points here, and we can give each one of those a row, right? Maybe this is on the what is that? Longitude of 71.5 degrees and latitude of 40.2 degrees or something. And so it gets its own row. You get this second point, that gets its own row, and you get this third point, and that gets its own row. Makes sense, right? It gets wonky when you hit other types of data, though. Lines are essentially things that connect several points. And we actually take that information and we just shove it into one row of our data frame. You can kind of see that there are 3 different coordinate pairs here, 3 different XY pairs in here, connecting from one line to the next to the next. But we kind of push that all together and stick it into one row. And finally, we got polygons. And polygons are even weirder. So these are the same thing, except that as opposed to a line, eventually it finishes. So you notice there are 4 coordinates, because there's the first one, the second one, the third one, and back to the first one. It is not deeply important to me that you know how to make points, lines, and polygons. Today, I will be sharing with you some points, lines, and polygons that I have made. But it is helpful to know how they are structured so that we can work with them in the future. So to summarize, points get 1 row each, lines get 1 row each, and polygons get 1 line each. Make sense? What's really cool about this is we can start doing some really amazing work with points, lines, and polygons. We can, as you've read about, map all of the green spaces, the parks throughout New York City. We can visualize every household in South Africa, for example, as we've seen in this map of Cape Town below. We'll be talking about those more during our reading questions today. And so just a quick question. Of the 3 types of spatial data here, what do you think, what type of data is going on in our green space map up in the upper right-hand corner? Anyone want to shout it out? Is it a point, a line, or a polygon?
Polygon?
Yeah, polygons, exactly. Fun thing, you can usually change the fill of polygons, which is kind of nice, and you can do a lot of color working with them. Thanks, Camila. And so if that's a polygon, what's going on in the lower right-hand corner? Shout out.
Points.
Points. There you go. It's helpful. It says a dot map too, right? We can sometimes use different terms for it. So we've got the main idea. Geographic data is funky, but it still fits into our framework that we've been learning about this entire term. It can all be encoded into data frames. So, just a moment. There we go. The question is how. It can be really tough to encode this into a data frame like a CSV file that we've been working with so much. So we actually use a new type of file format. It's called a Geo Json. And the idea here is that this is a special type of CSV that can actually handle, it can nest multiple values within one cell. So it's great for points, lines, and polygons. You can kind of see in this example here that we've got like the longitude and the latitude, and they've all been nested into one cell right here. We usually use read CSV to import this data, but in this case, we're going to use something called read SF. It's a new function from the SF package, which is sort of like the tidyverse, but for mapping. So we're going to be using the SF package. We're also going to be using a package called GG Spatial. And these are sort of the 2 extras that we're adding to our toolkit. So let's walk through a couple of examples of this. So in this workshop, we're thinking about social infrastructure. This is my current sort of focus of life, because social infrastructure is this idea that there are places throughout our community that build social ties. There are community spaces like libraries, places of worship like mosques, synagogues, and churches, social businesses like cafes and Dunkin' Donuts, and parks, and fountains and squares and all these places. These are places that allow people to come together and be, allow them to make ties, which we know is really important during this crisis. And so we might start to wonder, hey, do some neighborhoods have more of these than others? You may have wondered about this implicitly. I've been wondering about this a lot ever since the pandemic began, and I started to realize, oh crap, the area where I lived had very few social infrastructure sites. It was kind of hard to gather with others in a safe way, outdoors or that sort of thing during the pre-vaccine months. So I started to wonder about this, and together with master's students and undergrads, including some people on this call, we have been working to map all of the social infrastructure in Boston, which has been no small feat, and I really appreciate their efforts. So props to Olivia. So the idea here is that we've been able to take a lot of these sites and put them all into a Geo Json file so that each row is a point, a social infrastructure site. And when we read this in with our read SF package, it's going to look, and we can check what's inside it with our head function. It's going to look a little different than our usual data frame. So for instance, we've got this part here that says geometry type point. Helpful. We've got this part that says bounding box. This just gives us a sense of where all of our points are. It's a little box that says all of my points are within these coordinates, this longitude, latitude set. And last, we've got the data frame. You can see here, this is the first 3 rows. Anyone been to the Christian Science Plaza? Yeah, that's kind of near the big reflecting pool, just across from Mass Ave, right? And kind of Symphony, T-Stop, that area. So the main difference between our other data frames is that as opposed to just having rows, we've got this extra column at the end, a column called geometry. And just like we've been talking about, this column has an entry for each row that specifies its point in space. So this is fairly common when you start working with new types of data like spatial data or network data, et cetera, there will be some extra columns that you haven't worked with before, but they usually follow this kind of format. It's just some special attribute, and it now works with all of the functions that we've been working with up until now. Okay, so we've got our points, got these points throughout space. We've also got polygons. In this case, it's a data set of 1 square kilometer grid cells in central Boston. Each one of them is about the size of a city block. So in each row, we've got basically a bundle of coordinates that makes 1 polygon, and each cell has a number, okay? And so we're going to call that my shapes in this workshop. We've also got some census data called my data. And this is just a data set of average traits for each grid cell. So things like population density, the percentage of residents who are women, the percentage of residents who are white, the percentage of residents who are black, et cetera, okay? These are essentially the variables that you get to work with, fun fact, for the lab. Our lab is going to be a little open-ended in that regard. Hey, I'm seeing some a note from Elizabeth here about polygon points. Any questions? Feel free to jump in if you have any questions.
Those were just the answers to the questions you were asking earlier.
Oh, thanks. Appreciate that. Okay. So here, for instance, we can see that there's a unique ID, right? In the cell column, we got cell 100, cell 106, and then there's all of this crap. So you may already be thinking, hey, wait a sec, I know what to do with this. We're going to join this in to that polygon. Yes, I know your favorite part of this course, left joining, is back. Next, we got one more type. This type actually isn't very important. It's lines. We don't do as much with that in this workshop, but it's kind of nifty. This is the T. This is a data set of train tracks, right? So each line is a part of the T system. It's a part between 2 T stations. And so I've got one variable here called line that is going to tell us what, let me just try that again. There. Got a little bit of a delay here. Brief pause. There we go. Okay, we've got this variable that tells us, is it the blue line, is it the orange line, the green line, the red line, or the silver line, right? And we got that geometry column. Doesn't really matter what's in there. We don't actually interact with that part, but that tells us where our points are in space. So we can use this data and overlay it. And we can use this cool function called geom_sf. So when we're working with geom_sf, we first make a plot using ggplot, as you can kind of see there in the upper section right here. And then we add something called geom_sf. Now, we know that using ggplot is going to give us a blank plot. It's just going to blank plot up there. And then when we add geom_sf, it says, hey, R, you should be interpreting this as geographic data. So we can say data equals my shapes, the name of your Polygon data frame. We can give it a fill, give it a color, give it a size for the thickness of that outline. And we can repeat that for points, saying, hey, our new data is my points. Please put those on top of what you've done already. Please make their color be Dodger blue and make them a certain size, make them a certain transparency. Transparency is great with maps. And finally, we can use, we can overlay some lines. I must admit the T-system does not look as good in this visual. Sorry. I think there were some issues with that, but we're just gonna roll with it for the time being. So basically, order matters. You can layer other types of data on top of each other. Fun fact, this is how ggplot actually works. You can do this with anything. So if you wanted to produce like a violin plot on top of a box plot, or put different data frames into your ggplot, you can actually do this too. You just need to say, instead of geom_sf, you'd need to say geom_boxplot or that sort of thing. Okay, so this is a little glimpse into the deeper inner workings. But let's be honest, that map looked kind of crappy. It was also really zoomed out. We might want to zoom in. We can do that by cropping. We can tell ggplot, hey, it's okay, just zoom in a little bit. We can do that using the coord_sf function. We got this thing called xlim, where we say, hey, zoom in so that the x-axis is just within this range of coordinates. And we can say, hey, ylim, please zoom in so the y-axes are just within this range. We can also do things like adding a nice clear theme, adding a scale. That's where GG Spatial comes from. It gives us our annotation scales. You can see in the lower left-hand corner, there's this little 2 kilometer mark there. We can add some labels. Yeah, Vincent, what are you thinking?
So when I was doing this, like with the workshop over the break or whatever, I was thinking, like, for this to work, does the like shape data have to be like already within the same coordinates that we're zooming it into right now?
That's really neat. So in this case, no-ish. Your shape data could be in a different coordinate space, in which case, if you zoom into this part and your shape data is actually over here, you will see a blank white square. It's very problematic. So it is sort of agnostic about the location of your data. So if this happens, it might be a good idea to check out your bounding box and see where actually is my data. That's why I like using theme BW. It allows us to see actually the longitude and latitude coordinates. Obviously, though, we do want our polygons, our lines, our points to be within that area. So we want to identify kind of what area they're probably in, grab that one, and put that in our bounding box. You'll notice that even polygons that are a little bit to the side are still getting included. So the whole thing stays in, even if part of it gets cut off. Does that make sense?
So like if you were gonna do this all like from scratch, then you would have to like do the shapes like within the coordinates like that that you're gonna be looking at like later. So it all start like line up in the end. So the fact that you had like the first map like kind of zoomed out was like not too good, because then you could just like go further and like use the same coordinates in both like parts, so that you like are just looking at that.
Exactly. And I'm really glad you brought that up, because you know, some people have this deep innate sense of geographic coordinates, and I do not. I never remember where, like what latitude or longitude my points are in. I'm always forgetting this sort of stuff. So I always just plot it first without the crop. I look at it and be like, huh, okay, 42.38, cool. And then I use that to kind of guess by trial and error, what is the best box for me? Okay, so it really is a game of trial and error. But as you'll notice, we're zoomed in. It looks a lot better than it did before. Doesn't look awesome, but it looks a lot better. So a couple extra things. This is a kind of fun one that works outside of mapping too. You can layer data to get outlines. Whoops. So these are our grid cells. This is kind of the core of Boston. It kind of reaches down. It includes like Dorchester, the North Ends, Fenway, and Mission Hill, JP, but it excludes everything else. I'm sorry, Alston. And you'll notice here, I've said, hey, first I'm going to make a really big version of my shapes where the size equals 10. So it's got a real thick, dark gray outline. And then I say, hey, make a new one. But this time, make its outline be very tiny and maybe a different color. I'm essentially taking one version and layering it on top of it with just a slight difference in the outline, so that I can get some nice outlines that are difficult to get otherwise. You can do this sort of thing with geom point as well. You can do this sort of thing with geom box plots. Any of that works. Any questions about this? This is just a little trick. Comes in handy with mapping. Finally, we've got this issue, which is that we could put all of this data on, and we could actually map its aesthetics and all of that. And I could have remembered to animate these little text boxes and asked you what's wrong with this visual, but I did not. And so instead, what do you think? We can see that there's a lot of clutter. There's no sense of place. There's just a lot of information. The color choices don't really match. Any other comments? Anyone want to diss this visual with me for a moment?
The lines for the T are like a little thick.
Mm-hmm. Lines with the T are a little bit are a little too thick, honestly, right? You'll notice they do have a nice little layering thing going on there, right? We've got a little white outline, but it kind of obscures. Plus, you can't see them most of the time, right? Any other thoughts?
Yeah, I was just gonna say that the points are too like solid. They should be a little more transparent so you can see what's underneath them.
Agreed. Agreed. Any other thoughts?
The x-axis is overlapping.
X-axis is funky. Yeah. And Ava, what were you gonna say?
I don't know if it's like under the same thing as the color, but maybe like for the lines, it should be the same color as like like I know like there's an orange line, but it's not the like right orange of what it actually is.
Yeah, yeah. There are certain deep meanings to colors, and like getting them right kind of matters. So in this case, we might look at this and say, there's so much data here. Maybe this isn't maybe this isn't the ideal way to visualize this information. You know, we could take away the lines, but honestly, that doesn't really help as much. Olivia just mentioned Maybe you might facet wrap by the type of social infrastructure. I would agree. That's a great way to do this. So that might reduce some of the density, right? There are a couple different ways that you can handle this, but this probably not the right way. One way that you can handle this is by, if you've got too many points to make a meaningful map, you could just tally them up and visualize it, use them polygons instead. So, for example, let's say you got 2 grid cells. I think these are the grid cells in our map that's northeastern and like right next to it. And it's about a square kilometer, and since nobody knows metrics, that's basically a city block. Let's imagine that we got 3 points in cell 123, A, B, and C, and we got 1 more in D. Currently, these are in different data, right? So we can say, hey, I'm going to filter my polygons to just be these 2 cells. Great, we're going to call that 2 shapes. And then we've got all these points in my points. We want to make a new data frame that gives us a row for every single point, like this. Because if we get this, we can summarize. We can summarize really easily. So we can do this by doing something called Spatial Join, or joining spatial data with ST join. It's made to be a lot like left join. The difference is, when we used left join, we would take 2 different data sets and join them together using a shared identifier, like a unique code for each county or each municipality or each person. But in this case, we've already got that unique identifier. We've got geometry, right? Our geometry column. And so ST join knows to look in that, and it says, hey, is my point inside this polygon? It returns, in this case, all of the points that are inside the polygon, the data frame 2 shapes. And you can kind of see, okay, we've got 3 rows, 1 for each point now, 1 for each polygon, but we've also got now the cell that it's in. This is like a little boring, but is honestly the most important part of GIS, of geographic information systems. Counting stuff is the whole name of the game. We want to know how many Dunkin' Donuts are in the downtown. We want to know how many patients, how many COVID patients are in this neighborhood versus that neighborhood. We want to know how many households got access to SNAP benefits, for example, right? So once we get this data frame, we can just go and do our usual stuff with it. We can group by each cell and count up how many points match a certain condition. And there should be one more thing here. Here we go. We can get this kind of table. So sometimes the tricks for counting can be as simple as using the n function that we've used before to count the number of rows. Sometimes you might want to count very specific things. In the past, we worked with the filter command, and we learned that you can use these operations. You can actually do some really cool things with them. And this is just the tip of the iceberg. But for example, one of the variables in our myPoints data frame is called group. It tells us what type of point it is. Is it a place of worship? Is it a park? Is it a community space? Is it a social business? So we can say at the bottom here, we can go by each row and say, does the group equal parks? for every situation where the group equals parks, we're going to get a 1 or a 0. That's what R does whenever it looks at one of these phrases. Technically, everything that you're doing with filter is you're saying, hey, in what cases is this true? Give me a 1 or a 0. And filter is saying, okay, I'll just take the 1. I'll just take the ones where the answer was true. True equals 1, false equals 0. So we can essentially say, hey, take the sum of all of these rows of true or false, convert them all to 1s or 0s, count it up, and that's going to be our total number of parks. Now, there was a lot in there, so I'd like to pause and ask any questions about this. So in the past, we used filter, like filter to just points that equal this condition. But we can also use it in summarize by saying, please find for me, is this a park or not? Park or not, park or not, park or not. Now count up all of the cases where that was true. And that's going to give us our value that says there are 8 parks in cell 1, 2, 3. I couldn't draw them all in this case. And there are 11 in cell 1, 2, 4. We can also do some cool stuff with NAs. If you just want to count overall how many there are, you can always say how many are not NA, right? Because if they are not NA, non-applicable, then they are present. You know, it's kind of like saying, are you here? And so that's a good way to count total. Okay. So you can imagine, and you might want to be thinking, it seems interesting that he's focusing so much on this. Maybe this is in the lab. You can count up the total number of social businesses in your data frame. You can count up the total number of community spaces, the total number of places of worship. You can see how this starts to get powerful real fast. And it can give you visuals like this. I really like this one. We can see at the top, we just did everything we just spoke about, but we did it for every polygon. We said, take my shapes, join in my points, group by the cell, and count up the total points and count up the points where the group equaled park. After that, you can even go ahead and start adding in new things. You can left join in all of your data. You can get a rate for your total and your parks by controlling for population density. In this case, it gives you a really tiny number, so it's helpful to control for it in thousands, right? So we're dividing population density by thousands, which is the same thing as multiplying the whole thing by 1,000, okay? So this allows us to get really pretty smooth rates that count for population so that we're counting, say like once we take population out of it, which of these neighborhoods have the most social infrastructure? We know that places with more people probably have more social infrastructure, right? More people, more taxpayers, more parks. It's kind of a pretty straight thing there. But it allows us to start making inferences like here, where we see that this little section in the lower left has a very high rate of social infrastructure. I think that's near the Jamaica Way. We can see that this area up here in Back Bay has kind of a surprising lack of social infrastructure, whereas this area near the Boston Common, you can actually see the Boston Common, or maybe that's the public garden right here, has much more social infrastructure. So you can start to see how these kinds of techniques can be very helpful. Okay. The way that we would visualize a trait like this would be by taking a data frame. In this case, I named what we made before my rates. So you can take that data frame. You can say mapping equals AES, just like we always do. And you can use the fill. So fill equals your total rate now. You can also do some cool things like setting the color to equal NA. It has to, it can't have quotation marks, FYI. But if you do this, it's going to remove the outlines. You can add a few extra things, and you can get a pretty plot like this. Last, you can start doing some nifty things, some supplemental analysis. For instance, as we might want to just say, hey, I don't actually care about this being a spatial data frame anymore. I just want to analyze it like I usually do as a normal data frame. So we can use this as Tibble function to convert it to a normal data frame. We can get rid of the geometry. We can filter into just the cells that have people in them. And we can start doing things like getting the mean. We can find the mean rate of social infrastructure for every neighborhood. This is a cool plot. And once we do that, this is just a geom call. You guys know how to do this. You've been doing this all term long, you know? We can start finding some really interesting patterns from geographic information just using the same toolkit we've been using this whole time. So we can see that South Boston is pretty well-to-do and has a lot of social infrastructure. We can see that the downtown, kind of same thing. This uncomfortable trend that wealthy neighborhoods tend to have much more of these places that support our social life. Yeah, and so I think that's about it. There are several extra analyses that we do in the workshop, but this is here to give you a sense of what we're doing and to show the key steps. We visualize, we spatial join, we make it a data frame, and then we can do whatever we want with it. And that's kind of the pattern with geographic information. So I hope this has been interesting. And I'm going to turn off the recording now.